what we will do today is to see the power of multiplicative weight update. This is like a warm-up, basically. And the warm-up is already like quite powerful, which is to solve any LP, approximately. So let's recall what is weight update, right? The algorithm is an algorithm that with the parameter epsilon, you just initialize the weight on every expert to be 1 uniformly. And then for each day, what will happen is that you will just choose each expert I with probability proportion to the weight. And after that, once you have commit to your probability, then some loss vector on each expert will be reviewed. And what you do, you just update the weight accordingly. If the loss is big, you decrease the weight a lot. Okay. Update it multiplicatively. And what you want to compare is basically the loss that the algorithm makes, the loss of the weight update algorithm, which I will this is just a sum of the loss of the weight update algorithm on day t. And how did we define this? This is just like the inner product between the probability and the loss vector. Okay. This is from last class. And you think like this as expected loss when you choose the distribution P, and this is the loss vector. This is your expected loss on day t. So summing over all this is just our total loss. Okay. And we want to say that our total loss compared with any expert I, our loss is small. So the total loss of expert I use Li, which is the sum of the loss of expert I on day t. That's the total loss of expert I. And with update algorithm guarantee this. It guarantees that for any I, our loss compared with the loss of expert I, like we are as small as the loss of any expert I with some additive factor here. So that's from last time. And let me just write it in another way. Suppose that I write this thing, like I write this as like a list, a vector for the loss of every expert. Let L be the loss of every expert, the total loss of every expert. Okay. Now, then what do we have? We can just say that if you have any distribution of expert, okay, I can just say that our loss compare with like this average loss of our expert is just like this thing is less than this thing too. Just because we are like this thing is less than Li for every I. So we are even less than like the best I, the best expert. So even if you put this like this is just an average, right? This is just like the average loss, like weighted average loss of expert. So we would be smaller than that average loss as well. This is like nothing new here. Like that's not a deep thing. That's what I said. But sometimes it's easier to look at this formulation. Okay. So that's from last time. And now let's look at some linear program problem. So today what we're going to look at is look at this. So right from now I will write this thing delta n theta n is just like a set of probability distribution over n objects. It's just like a vector of size n such that everything is non-negative and the sum is 1. So now the problem that we're gonna consider today is this problem. Imagine that you have like a matrix. Think of this as a constraint matrix in the LP. So there are m constraints for n variable, right? But I promise that every entry in this constraint matrix is actually between 1 and -1. And you have B here. Now, let's say that what I want to do is just to check if there is a vector x that looks like a probability distribution such that A of x is less than B. Or just say that, okay, you cannot find such x. That's the problem. Okay. So, like normally what we have is like you kind of have like A of x at most B, maybe max CTX, this thing. So that you want to maximize something, right? Here there is no maximization. You just like kind of ask if there is some x such that it satisfies this constraint, okay, or not. Now I claim that if you can solve this one, you can solve this one too. Why? Because you can just say that, okay, let's ask if there is an x such that C of x is greater than something 10, and do some binary search, right? So you can do some binary search and then find like the best x such that this thing is maximized. So put this as like a sum, like include this as like another inequality constraint here. Okay. So you can think like you can check this, but you can try to do this at home. But my claim is that if you can solve this problem, you can actually solve any LP using binary search. Okay. And the solution will not be exact because you will need to binary search like over all this thing, but you can make it as accurate as you want. Okay. Yeah. But today we're just gonna look at this simple thing, this simple question, because it kind of fit nicely with our weight update algorithm. Okay, so that's the goal. Question about this goal? All right. Okay. So, and now what we're gonna do today is actually like kind of a relaxed version of this feasibility problem. What I'm gonna do is I will just find x that looks like a distribution such that it satisfies all the constraints up to some additive error, right? Like xa is less than b plus something. Like this is like all one vector here, plus like epsilon and all one vector. So for each constraint, I like satisfy it up to some additive epsilon. Okay. Or just say that okay, there is no feasible solution such that everything is really satisfied. So there's no slack here, but there is slack here. So if I find something, I allow some slack, or say that there is no feasible solution. And the algorithm is going to be so fast, so it's just gonna spend time proportion to, like, it's almost linear. It's linear time, basically. The NC of A is like a number of non-zero in A. So it's linear time up to something, up to some log factor in epsilon. Okay. So that's the goal. So let's see how do we solve this one using, of course, weight updates. And the natural idea is this. We're gonna do some kind of whack-a-mole. Okay. What we're gonna do is, like, let's start with some trivial solution and then check if there is any violating constraint. If there is any violating constraint, then we try to fix it. And how to fix that exactly? Use weight update. Okay, so let's see the algorithm. Initially, I will just set the weight of everything to be 1, just like in weight update algorithm. And then we will just set xt here to be like the weight after scaling down. So xt is just like pt in weight update algorithm. It's just proportion to weight, but you scale it down so that it looks like a probability distribution. So you have xt. So yeah, xt is wt over capital WT when capital WT is the sum of the weights. So you scale it down. Okay, now we're just gonna repeat for some days, for some rounds. And you first ask yourself, okay, if this solution, if this xt already satisfy everything up to some slack, if so, you're done. Don't need to do anything. Okay, just return x. But otherwise, then, okay, there is some constraint that is violated quite a lot. Some constraint must be violated by more than additive epsilon. Okay, so what you do, you just look at the constraint. There must be some one row it, such that this constraint is violated. Sorry, this should be it. This row is like when you look at this row, this is more than bit plus 2 epsilon. Right? Just look at the row that is violated by more than additive 2 epsilon. And once you see this row, what did I do? I just try to update it, like whack that thing. How? Okay. So I just gonna update this thing. Like the weight is gonna be multiplied by 1 minus aitj. So the intuition is this. So you look at this row, right? This row of A, this is AT. If some coefficient here is big, let's say this is big, this 1, like some one is small, like let's say 0.1. So the coefficient J here, that is like if aitj here is big, then this is like the coefficient that like make this whole thing big. So what you want is like to decrease x on the coordinate j quite a lot. So what you do is just, if this guy is big, you decrease the weight quite a lot. If it's small, then you don't increase that much. If it's even negative, then you can increase it. But the point is that for each guy that is big, you really like just decrease x a lot. So does this intuition make sense? Like, what you do is like, just update the weight on each coordinate j, like this. If the coefficient is big, decrease the weight a lot, and that will in turn decrease x in the next iteration a lot. So this is just how we fix, like we fix the constraint. We whack that constraint. Question about this step?
So when you update the little w, did you also update the big w?
Yeah, like big W is always like the sum of W at all time. And X is going to be WT over capital WT at all time. So you can think like only the weight change, and you maintain X and the big W like by using this equation. All right, so like find a constraint that is violated a lot, whack it like this, and keep going, keep whacking. And if somehow you can whenever there's nothing to whack, just return. Otherwise, if you need to keep whacking for like long time, just claim that okay, nothing you can do now. There is no feasible solution. Yeah.
So A between 0 and 1?
Yeah. I assume that, you see, entry of A between -1 and 1.
Yeah, sorry, yeah, I missed that.
Yeah. Okay, more questions? So like what you should have right now is just that, okay, this algorithm looks natural. Okay. Just keep fixing what you want to fix. Okay, now it's clear that the running time of the algorithm is just to multiply xt to a and check. So that takes non-zero of a time per round. And there are this many rounds. So the running time is clear. Okay. So what is left is just to prove the correctness. So my claim is that if actually there exists some feasible solution x star, that is like there exists the x such that this is true, such that all the constraint is really satisfied exactly, then it must be the case that the algorithm will return some x such that each constraint is violated by just 2 epsilon additively. Okay, so let's see the proof. So let's suppose for contradiction, right, that after t iteration, then like x is not returned, even if x star exists. So now let's analyze it. So the key thing to observe is that this whack-a-mole algorithm kind of implement weight updates exactly, precisely. Because how? Like you can think of each expert as like variables, right? So I mean we maintain that this we have this distribution x, which is proportional to the weight on experts. If you think of like this is a distribution on variables or on experts. And what do we have? We have like, what would be the loss vector that we get for each on each day? Claim that the loss vector can just look like the IT row of like of A, which is just a vector between -1 and 1, right? Why? Because like you see, normally in weight update algorithm, what we do is like we set the weight, we update the weight in this way, right? Oh, sorry, there should be minus epsilon here. Yeah, there should be epsilon here. Sorry. We update the weight such like this, right? Here's the weight T minus epsilon L JT for all J. So now like this LJT, the loss, is just this one. So the loss vector is just the IT row of A. Okay. So that's the loss vector. Okay. And then we just update the weight like this. Good. So this is exactly like the way we update XT is exactly how the probability distribution evolve in weight update algorithm. When the loss vector is just the AT row of A. So now let's see what we have. So on each day T, let's see it like you can say that the loss of the weight update algorithm is just the inner product between the loss vector and the distribution xt, right? So what's that? This is just like the row of A times xt, which we know by the choice of like this row. By the choice of this row, this is going to be more than BIT plus this thing. Why do we have this? Why do we have 2 epsilon? Because we exactly choose the row, right, such that this guy violated a lot. Okay. That's why we get this 2 epsilon here. But also, what do we know? We also know that actually there is the X star. There is a feasible solution, X star, such that when you multiply it by 2LT, this is just exactly the row of this row, the ith row times X star. But this is feasible. X star is feasible, so this must be less than BIT. But then what do we know here? What does it imply? It implies that when you when you compare our total loss of the weight update, and it's like the average loss of our expert, averaged by xt. You think of xt as a distribution of expert, right? So this is average loss of our expert compared with this, our total loss. This is just like the sum over all days, LTXT minus LTX star. Okay, this thing is always big, bigger than 2 epsilon, right? Just follow from here. This term is at least like a BIT plus 2 epsilon. but this term is always at most bit. So on each day, your loss keep getting bigger. Like the regret, the regret keep getting bigger. You have like a 2 epsilon that you get the regret for on each day. So you see now, it looks bad here. It looks like, okay, you run weight update algorithm, but your regret kind of grows on each day by 2 epsilon. But you know that weight update algorithm guarantee no regret. Okay, so it cannot this cannot go on forever. So just from intuition, right? You know from last time that the weight update algorithm should have no regret. It means that there should be some contradiction now. If t is kind of go on forever, if t is big, this regret is keep getting bigger and bigger. But you shouldn't have regret. So that's contradiction. So to make it precise, what you have is this, right? Just from the no regret bound of weight update, we know that this thing, when you compare the loss, our loss with the average loss of our expert, or total regret here, this should be at most epsilon t plus ln n over epsilon. That's just the bound that we get from weight update. But we set t here to be like a epsilon square, ln n over epsilon square, right? So this term is actually less than epsilon t is ln n over epsilon. So this is just epsilon t. So this is just 2 epsilon t. So that's the contradiction already. Because on one hand, you have that this term is bigger than 2 epsilon. On the other hand, this thing is less than 2 epsilon t. So that's it. Okay. So you see that if there is some feasible solution, then the algorithm must return some x such that you satisfy all the constraints up to additive epsilon. So just to recap, the idea is that every time that you whack, you whack the constraint that violate the constraint a lot. Each of the whacking here, every time that you find a constraint that violate a lot, right? You know that you accumulate epsilon regret on each day. So on each round, the regret kind of keep growing, but you know that weight update have no regret. So this cannot go on forever. And when you do the math, it can go on only for a ln n over epsilon square. Okay. So question. All right. So you might say, okay. So you see, what we have, the promise that we have right now is that you promise that a is between -1 and 1, and also we want to just find x such that it looks like the distribution. This might not be true in general. So what if I just remove this promise by saying that, okay, what if the entry of A is between minus row and row. And let's say that you still have some bound on X. Let's say that if you know somehow that there must be a solution such that each of the entry is at most, let's say, tau prime, then it means what? It means that the sum of X is at most tau prime times n. So then let's set tau prime times n to be tau. So you still know, you know that the sum of xi is still at most something. What if I just promise, there is no promise, but you can give some bound on each entry of A and the sum of xi. What would be the running time when you apply this algorithm? It turns out that you're gonna get something similar. You're gonna get this thing, but now this epsilon square, you will have rho and tau. This factor rho and tau here. So it doesn't look so good. Yeah. And the hint is just to set epsilon to be small enough, and everything will work out. You need to scale it down scale things down so that this thing, you start with A that is big, you scale it down so that A is between minus 1 and 1, and use this algorithm. So by scaling, then you can make it work. It's not that interesting, but you can check. But you can see that this is not so great because rho and tau can be big, can be huge. And your algorithm spend time polynomial in rho and tau. So that's not great, but there is a technique for removing this dependency. It's called width independent weight update. But I will not show it in this class. You can look up if you want to. Yeah. I use it in my work quite a lot. Yeah. Okay. So yeah, but you see, this might be the most natural way to solve LP, and you can do it using weight update, and it's so simple and it works. Okay. Right. So let's go to the next topic. What I want to talk about is game, the Minimax Theorem, and strong duality. We will prove both of them using weight update. So I promised you to that we want to prove strong duality at some point in class. Is today. So recall that strong duality says that of P equals of D, right? For the dual LP, when primal and when P and D are a LP that are dual to each other, then the optimal value are the same. Okay, so I will not recall this. So what we're gonna do is we're gonna go through games, game theory. Okay. So one of the most simple concept in game theory is zero-sum game, two-player zero-sum game. So two-player zero-sum game, and that it's just you can describe any two zero-sum game with one matrix. So you can think of one matrix, which we call payoff matrix. So it's just, maybe I put it here. You have some matrix, okay? Call it A. And there will be two players. One is a max player, another is min player. The max player will choose a row, I of J. Max guy choose I, and the min guy choose J. And once max player choose I and row player min player choose J, just look at the entry Aij. Then what will happen is that max will gain Aij, and min will pay minus, min will pay Aij. So the payoff of min is minus of Aij. So this is why they call it zero sum, because the sum of this is zero. Okay. So when someone gains something, another player must pay that amount. Okay. That's zero sum game. And every zero sum game is just one matrix, basically. Okay. So you can think of zero sum game is just a way of thinking, but formally it's just one matrix. So for example, when you have rock, paper, scissors, you have this game where, okay, if this guy chooses paper, this guy chooses scissors, then you get -1 because this guy, the max player, loses to the min player. Okay. Max player get this, min player get this. So the max player lose. So what max player want to do is to win. Maybe he wants min player to choose wrong. So this is a kind of a game that we all know. Okay. There can be a more non-trivial game. For example, let's say max is a game between two armies, let's say there is a war and max player have n armies, min player have m armies, m and m are not the same, and both players want to divide their army among two mountains. There are two battlefields. Okay. And let's say that max will lose if he is outnumbered on either mountain. Otherwise he wins. Then this game can be described using this matrix. This is max, min, and for example, if you look at this one, max put one army in the first mountain and 3, and min player put 2 and 0. Then max will lose because 1 is less than 2. Otherwise, so this is where max lose. This is where he lose. Everywhere else, he will win. That's just another example of game. There is one more, one very generic game actually, that will be related to us. That is for any computational problem. You can think of this as a game between us, algorithm designer, and the adversary. Okay. Adversary is a max player that chooses an input. We, the algorithm designer, is a min player that chooses an algorithm. And what we want is the payoff, to minimize the running time. So the payoff is just AIA, the running time of A on input I. So what we want is to choose some algorithm such that no matter what input is, this is minimized. That's a game too. Okay. All right, so we will look at this game more closely next time. But you see, when you have game, some game you cannot play deterministically. For example, in rock, paper, scissors, if you play deterministically, that's a really stupid strategy. If you always play, if I always play rock, then you lose, yeah. So it's bad. Okay. So what we want to talk about is a randomized strategy, right? So max player want to choose some distribution of rows, and I call it X. X is the distribution of row over n rows. And min player will actually choose the distribution of column over m columns. Okay. And once you have these two distributions, now we can think of the expected payoff. So what is it? The expected payoff, which I will use AXY to denote. The expected payoff is just a sum by j, the payoff, and the probability that xi is chosen times the probability, row I times probability of column j. So that's just this thing. And this is, you can write it down like a x times a times y. So the expected payoff can be written nicely like this. X times a times y, right? And when player play deterministically, let me abuse the notation a bit. That is when the max player choose I just use AIY, and the expected payoff is going to be basically this vector, the IE, like the IE vector times A times Y. So IE vector is just, the vector such that this is 1 on the ith entry and everything else is 0. We can just say, what about AXJ? This is just expected payoff when the min player chooses J deterministically. Right? Question about notation so far? Okay. So now let's start with some simple observation. Suppose that the max guy announced his strategy, which is X. He just announced his strategy, which is X. Then what is the best thing that min player should do? She should just choose the strategy with respect to X, so that everything the expected payoff is minimized. So in particular, what min should do, just respond to X, exploit this information of X, right? Min should just choose Y such that it's the argmin of AXY. In particular, suppose that you have but actually I claim that this strategy Y can be even deterministic. Why? Because when you have a vector A and let's say X is chosen, right? So you can just average this thing and you get this X times A, and that looks like one row now. Each of this this looks like the expected payoff that, okay. So now if you look at the entry J here, what does it look like? This is just the expected payoff to choose J given that max choose X. Right. When x is fixed, when you look at this row, you can just compare which one is smallest and choose that strategy that will minimize the expected payoff. So, make sense? When you know when Min know the distribution of max, just now she can just multiply x to a. Now it's just a n number that she need to compare. Just choose the one that minimize the expected payoff. So Min can just be deterministic and choose this one. Choose 1j such that this is minimized. AXJ is minimized. Right? Okay. So with this, now you can ask okay, if I want to write down what would be the max best payoff when he must announce his strategy first? You can write it down like this, right? You can write I will use this max min of A to denote this thing, max best payoff when he must announce first. That is, he wants to choose X, the strategy, such that it maximizes this whole thing, right? Because he knows that if he uses X, Min player will choose Y such that this is minimized. So he wants to choose X that maximizes this whole thing. In other words, and he know that we also know that if X is fixed, then Min player will be deterministic. So he just wants to choose X such that it maximizes this whole thing. So that, you see, this is just the best payoff that Max can get if he is forced to announce his strategy first. So can someone tell me, similarly, what should be the Min best payoff if she needs to play first? How should it look like?
Inside Minimax.
Yeah, it's just you just switch this thing. Okay. So similarly, the Min best payoff when she must play first looks like just switch this thing, right? Min first and then max, and then you get this. But you also know that if Min is chosen, if Y strategy is chosen, then the max player can be just deterministic too. So instead of writing this X, which is the distribution, the max player can be deterministic and choose 1I. It's going to be the same here. Okay, so that's So that's max min is the best payoff of max if he announced first. Min max is the best payoff of min when she announced first. So let me ask you this question. Which one is bigger? Okay. So let's see some intuition. The intuition is that, at least intuitively, you see max min should be small. Why? Because this is the payoff when Max announced his strategy first. Max shows some information, so he is at disadvantage. So the game should this should be small. Max is it's bad situation for Max. Similarly, min Max should be big because min is min is at disadvantage. She need to announce his strategy first. Right? So so from this intuition, you should think this max min should be small, the min max should be big, so this one should be smaller than this one. And it's true. And the proof is actually simple to verify. So why? Because if you look at any xy, okay, you know that, let's look at this a of xy. A of xy is always at least, instead of fixing y, you can just minimize overall j. This is also less than this one because instead of x, you can maximize overall y. Okay. So this is trivial, but this is actually true for every x and y. So here I can just maximize overall x. On this side, I can just minimize overall y. It's gonna still be true for every x and y. But what is this? It's just max min of A, and this is min max of A. So max min of A is at most min max of A. Okay, so we get some relation between these two. Okay. So now it turns out that they are the same. Okay. And this is called Minimax Theorem. For any A, max min of A is the same as min max of A. This is a theorem that is proved almost 100 years ago by John von Neumann. Maybe the best genius in history of human. So you can look up his story, but yeah. So it means what? From now, because min max of A is the same as min max, I can just define, for any A, I can define some unique value to this game. Given any game A, I just define value of the game to be this thing, min max, which is the same as max min. This is called value of the game. And let's interpret this thing a bit, right? What does it mean conceptually before we prove it? It means that it doesn't matter at all when you are in a zero-sum game. It doesn't matter who announces strategy first. There always exists an optimal strategy such that even if you announce it, distribution, even if you announce that distribution, it doesn't give you any disadvantage. Okay. So, and the best payoff of both players, you can determine it. It's just the value of the game. As long as both players are rational, right? If they're if they are not stupid, no matter what, the value will be this. The payoff will be the value of the game. If they both want to minimize and maximize. And yeah, so this is proved by von Neumann some years ago, almost 100 years. And it's really the starting point of game theory. Okay. And this is not clear. That is true. Some mathematician before actually tried to prove it, given some complicated proof, and proved that this is true for 5 by 5 matrices when A is small, and thought that it's false in general. But yeah, it turns out that this is true for any matrix. Okay, so, and why do I talk about this? This is because strong duality and Minimax theorem are actually equivalent. One direction is easy. you can actually show easily that strong duality implies Minimax theorem. And how do you do this? Well, you can try to do this at home, but the hint is that you can consider some LP for finding the best strategy for Y, for mean player. You can write it like this. You want to find Y such that for every row of AY, this is minimized. So you want to minimize V such that every row of AY is small. And Y should look like the distribution. So you see, this is like LP for finding the best Y. If you look at the dual, it's going to be LP for finding the best X. And because of strong duality, the value here will be the same. And it implies Minimax theorem. So that say that, okay, if you assume again strong duality, Minimax theorem follows. But today what we're going to do is actually we prove another way around. Because Minimax theorem also implies strong duality, I will omit the proof because it's not that intuitive. But it's true. And we will show how to prove Minimax theorem. And so that gives the proof of strong duality. Okay. So, okay. Question up to this point. So that's the goal. We want to prove this theorem. Question about the setting, notation. All right. Okay. And of course, the proof is using weight update. Okay. So, and it's gonna be algorithm, very algorithmic and really natural. Okay. So what we're gonna do is let's say by scaling again, I can just first just scale down the matrix a bit so that each entry is between -1 and 1, because this is the regime that we can work with easily. And now we're gonna look at this algorithm, greedy versus weight update for given A and epsilon. And this is gonna be some repeated game between max player that act like a greedy guy, and mean player that act like a weight update. And they will interact on each round. And at the end, everything, their strategy will converge to the best strategy. And at the end, it will prove Minimax theorem. So let's see the algorithm. Okay. Algorithm is like this. Start with again, I use the weight. Initialize the weight to be uniform weight, all 1. Okay. And the weight, total weight is just WT again. Now there will be some rounds for each day that there is day T. So what min player will do, he try to choose the distribution according to weight update algorithm. So min player will just choose Y, which is proportion to the weight. And he just announced this thing. Announced that he's gonna play Y on this day. And if this min guy announced the strategy, we know that, okay, the max player can just respond to that. Just be greedy. Just choose the best role, such that given that you know that min player plays Y, YT, just choose the best role that maximizes this thing, right? So just choose IT that maximizes this thing, and then the strategy here is going to be deterministic, EIT. Just be greedy according to YT. So that's the strategy that both gonna play on each round. And once you choose the min, choose this Y according to weight update. Max be greedy. And then after that, because min player want to be weight update algorithm, so he need to like define the loss vector and update the weight. How exactly? Well, just look at, okay. So min player choose yt, which is like a distribution of this. Max player you choose it. So now the loss vector is just going to be the it throw to the min player. I will just define the loss vector lt to be this row that the max player choose, right? And that makes sense because if some number is big, here it means that min player lost a lot. So this is the loss vector on the AT, and the min player just update the weight according to weight update algorithm, like before. If the loss is big, decrease the weight a lot. Okay, so just update the weight on each column. And then for the next day, after update the weight on each column, just choose the new distribution of columns after updating the weight. And this go on for a few days. And after that, what we do is just, okay, look at the max player, just look at everything that he chose so far on each day, average them out, right? This is just the strategy of max player on day T. Just sum them up and average them. For the min player, just look at everything that she did, average them, and then return. Okay. And I claim that actually, like, once they return this is going to be like basically the optimal strategy for both of them, and that will prove with a Minimax Theorem. But before we go to that proof, is this algorithm clear? It's just an interaction between greedy guy and weight update guy. Just play with each other until at the end, just average everything that they did so far and return the pair of strategy. Okay? So now my claim is this. My claim is that this algorithm will return a pair of strategy x and y such that this is basically the payoff of min. Min pays off after announcing y. When choose y. This is max pays off when choose x. So min pays off when choose y is like is small than max payoff when choose x. So you see, like normally when min player like choose like announce the strategy, min is at disadvantage, and it should be big. But here we get an upper bound of that big thing. On the other hand, like this thing should be small, but we get a low bound of it. So you see that this should lead to like a Minimax theorem. If not, it's fine. We will just prove it now. Okay. So what we're gonna do is just use it to prove the Minimax theorem now. And after that, let's interpret this lemma a bit. So the proof is this. So, well, given this thing, right? Odd, which is exactly this one. Suppose that here, I can just say that, okay, let's minimize over all y. And minimize over all y, this is gonna be less than this one. Let's maximize over all x. Instead of fixing one x, I get this thing. Okay. And what is this? This is min max of A. This is max min of A. And because we are free to choose epsilon to be as small as possible, if epsilon goes to 0, converge to 0, it would just mean that min max is at most max min. But we knew before that max min is always at most min max. This is the easy direction that we prove. So this together, it just implies the theorem. Okay. And now, like the interpretation of this thing is that, okay, we know that, okay, this thing is the best payoff of max when he announced x. But you know that, like, okay, maybe I write it down like this. This is the mean payoff when she announced y. This is the max. But this is our at most value of the game, right? Like this is just like a one strategy of x. This thing is at most the value of the game. So like it's like so y is a strategy such that even if when she announced it, this, like, no matter what y is, it's always at most the value of the game. So this, even when min announced it first, there's no way that max can gain too much advantage because this thing is like is still bounded by the value of the game. So it's just some interpretation. You can like look at this interpretation later, but let me try to prove this key lemma. Okay. So okay. But okay, the point is that both x and y are really kind of near optimal strategy, and like it's like by repeating the game for the few rounds, like kind of both players kind of converge to the best strategy. And this may be surprising for Greedy because it's like Greedy really like do nothing nice. Like it doesn't look like a clever like weight update, but we know that as long as its opponent is a weight update. If we just be greedy, then your average strategy at the end will be near optimal. Okay. If both players being greedy, I don't think like this will not like converge to anything nice. Anyway, let's prove this lemma quickly. So we should think like from min perspective, right? Min player want to choose distribution of columns. So think of columns as the expert. So there are m experts. And min want to choose distribution of expert. Oh, wait. What happened? Okay, back. Okay. So mean player will choose distribution of expert, and it like weight update algorithm guarantee you that the regret is small. The loss of the weight update compared to with the best strategy, like the loss of the best expert, this thing when you compare it, this regret is small. So the plan is just kind of to use this bound to prove this key lemma. This is our key lemma. So we will just basically try to connect this thing with this thing and connect this thing with this thing. That's the plan. So let's do the first thing. This is the second thing. Okay. So let's relate the loss of the weight update with like a max of aiy. Okay. So what do we know? When min choose yt, max will choose like the best strategy according to yt. So it. So it means what? It means that the loss of the min player on day t is just this one, right? So like AIT row, this is our loss vector. Remember, when the max player choose AIT, this is our loss vector, and we basically like choose this distribution according to YT. So the loss on day t, LT, and YT is just this thing. This is just a loss, like this is just a loss if the max player choose I and we choose the YT. This is a loss if the max player choose I, but max player just try to maximize this thing, choose the best, choose the maximum I, such that this is maximum. Okay, good. So now, so that's the loss, and so like the loss on each day is just a sum on each day, max I, AIY, and you can like, if you instead of sum of max, if you choose max of sum, this is gonna be lower. Like you can put this as a lower bound, and then okay. And then you get this thing because YT, like Y is just the average of YT. Okay. Sorry, I need to rush a bit because let me kind of go through it quickly. So similarly, like when you try to relate the L star with this thing, you can just compute the total loss of expert J, and you can like follow the calculation. Maybe do this at home. Sorry, but like you follow the calculation. The loss of the expert J is just gonna be T times A xj. So the loss of the best expert is just minimized over all J. So T times min J, this thing. And when you combine both together, right, you get that instead of like you have this is at most like you get the lower bound of this thing and you get the upper bound of this thing. The lower bound of this thing is like a T times like combine this thing together, you get this thing. So now you just rearrange, divide it by t, and because t is like this big, you get this thing, the key lemma. Doesn't matter too much like why this is like how you follow the algebraic thing, but the point is this. The intuition that you should have is that, okay, Min, once she chooses the best column, the best strategy, but she doesn't know which one is the best. So she just chooses the distribution of columns. The way she chooses is to use weight update, which have no regret. So if she follows this way of weight update, she will have no regret. It's as if she knows the best expert. So her strategy at the end, after averaging, it will be the best. So this is the intuition that you should have, right? There's no regret to use weight update. Or even if you don't know the best strategy, the best column, it's fine. Okay, and that basically that's the intuition that why it's good to follow the distribution of weight update when you have no idea which one is the best strategy. What's the running time of this whole thing? There are just this many iterations, and on each iteration, right, max player need to choose to solve some argmax question. And let's say that running time is denoted by max greedy, and then the min player need to update the weight, which is linear in the number of columns, which is m. So the total time is just time to update the weight, time to be greedy, and some log factor, which is the number of rounds. Trivially, a max greedy can be done in mn time. Why? Because all he need to do, right, is just to multiply, given yt from min, just multiply yt to a, right? This multiplication is matrix vector multiplication. That takes mn time at most. And then choose the best I. Choose the best entry, the maximum entry of this vector. So this is always at most mn. But it can be much smaller sometimes. And you might ask, okay, what if we switch the strategy? What if we let, instead of greedy, instead of greedy weight update, what if we just define weight update greedy? Just switch the strategy between max and min. Let the min guy, this is the weight update, greedy. Now let max guy be the weight update and min guy be greedy. It's just gonna be fine. You can define it similarly, and you get the same property. Okay. So next time we will see application of this thing, the fact that you can solve zero-sum game fast will imply one of the simplest flow algorithm and many other algorithms. Okay. So today we will see how to solve Minimax Theorem, right? Let me recap in 1 minute. Given any payoff matrix for the game, if you want to get these two algorithms, greedy weight update greedy, you can view it as a reduction. That is, if you just want to get some additive approximation of this max-min problem or min-max problem, phi x such that this is maximize this thing, phi y such that it minimizes this thing. At the end, you just need to be greedy on each round. You just need to solve to solve maximization of this thing for each round or minimization of this thing on each round. And the total time is either this one or this one. Actually, let me recap this next time. See you next time, and we talk about application of Minimax Theorem.